All right, the last thing I want to talk about today is how rocks melt and the process by which they melt. And they do this through something called partial melting. Take two different metals. Will they melt at the same temperature?
No.
Very good. Bismuth, for example, is a lab-grown mineral because bismuth is typically not really found naturally as a separated element, but it's used a lot in sprinkler systems for fire safety. Why is that? Why would you build, you guys ever seen those sprinkler heads that drop down the ceiling? Why would you build those with bismuth for fires?
It's harder to burn.
What do you mean harder to burn?
It won't melt and then close off the water.
There you go. You want to make sure you're using a metal that has a very high melting temperature, because if that starts to melt, what have you just done?
You just block the water.
You just blocked the water from getting on. Now there goes your whole fire safety. So they had to find a metal that has a very high melting temperature, so they make it with bismuth. That's you guys thought science ever went into this. All right, so partial melting. So we understand that different things melt at different temperatures. And that's the concept behind partial melting. Basically, what I want you guys to remember about partial melting, and we'll kind of make this very short. So different minerals melt at different temps. Okay, so different minerals melt at different temperatures. So let's say I take a rock and I have this really awesome kiln that I can kick up to degrees that are very similar to the interior of the Earth. What's going to happen? Tell me what I'm going to start seeing over time as I keep going back and watching this thing being heated up. What starts to happen? What do you guys think is going to happen? Thanks for listening.
I heard what you were saying. That,
Shut up.
So suppose I take a rock,
oh.
okay, and I go put it in this oven, and I just start turning the oven on. What am I going to start seeing as time progresses?
The rock is starting to
What? Which minerals? Not yeah. It's not. Now you're thinking a little better, but it's not just the outer ones. It's the ones that have what? Have a low melting temperature. Okay. So if my minerals have a low melting point, that's the temperature I'm going to come to first, right? So therefore, those will start melting once I hit that. And then my minerals that have a high melting point, those will be the last ones to melt, correct? What you guys have just figured out is smelting. You remember that before? That's how we take iron ore and get iron, right? We pulverize the iron ore, and then we send it into a kiln, and we start melting the iron out of the rock, and then we collect the iron.
Like in Minecraft. I always wondered what smelting meant.
That's what smelting means. You're literally taking the rock and melting the minerals out of it, and then all you have left is this rock. So that's basically the way we get that. Now, the reverse process of partial melting is fractional crystallization, which basically says this, right? As the temperature goes up, eventually what has to happen? It's going to go back down, right? Who are the first minerals to crystallize in that environment? Okay. Who were the minerals that were the last to melt? The ones that had the highest melting point, right? Okay, so then as my temperature starts to drop, who's going to be the first one to crystallize? The one with the highest melting point. So again, fractional crystallization basically says that minerals
It's right there.
with the highest melting point crystallize first. What kind of makes sense, right? Because as that temperature starts to drop, right, high, really high melting point, there goes my temperature, boom, this starts to crystallize right away. And the little guy down there with like 100-degree melting point, it's going to take me a long time to get to that. Now, let's talk about geodes. Notice how we have layers? Can you guys see the little concentric layers within that? You guys see in the back? Okay. What that is you have fractional crystallization within a confined space. Because if you have that, then imagine this thing sitting outside, the inside is still going to be molten. As it cools, the crystallized minerals start attaching themselves to the exterior walls. And so you get a layer of this rock mineral, then a layer of this mineral, then another layer of that mineral. And eventually you get down to where you have quartz at the inside, which has one of the lowest melting points. Okay, so that's how you get these layers within that. Now, we talk about this one. We say, well, how'd you get the calcite to show dead center of this cavity? Same concept. You have fractional crystallization. This material crystallizes first, leaving the molten calcite, which eventually then, as that's the only thing left, then it crystallizes in the center.
So is the composition of all of those crystals the same, or like how does it go from one crystal to different to like the calcite?
It is based on the chemical composition, and that then determines the melting temperature. Okay, all right. Imagine this: it's the melting point, or like the magma, in completely molten state, is like this soup. Okay, it's just a soup of tons and tons of minerals, and they're all in a molten state. Well, what happens then, if you start dropping the temperature, then you are below the melting point, so now those minerals that have a really high melting point, they start forming together.
Okay, that's
All right, they start to crystallize, and all the crystals start to hang out together, and they form this layer on the geode. Okay, and then the next layer forms from a different mineral because it has a different melting point. And then you get another layer.
That's right.
Okay, does that make sense now?
Yeah.
And I'll also be right with you.
Alright, you're fine, Dick.
Alright, and well, we already talked about this. So basically, right, partial melting is what gives us the idea of the smelting process, right? That's where that all comes from. Okay. In fact, let's talk about gasoline for a minute. This is very similar to how we get gasoline, right? Because basically, see how I'm going to do this without getting too political.
That's okay.
So our oil companies, right? We see them as these big evil corporations, right? Okay. How much do you pay for a gallon of gas or a gallon of milk?
Oh, down
$4.
Pretty
What?
close, yeah.
Yeah, they raised the price.
At Aldi's is way cheaper than.
I know. Okay, but what is your
So,
average
$2.
gallon of milk?
$4.
$2 to $3, right? And you get a little bit cheaper, but yeah, if you go with the name brand, you're paying $4 for a gallon of milk, and nobody says anything. That's okay
It's a necessity.
because it's a necessity, right? So it's okay to charge $4 for a gallon of milk that you get from squeezing it out of some animal. Okay, whatever. So that's okay. But to ask somebody to drill several miles deep within the mantle of the earth, pull out petroleum, pump it several hundred miles to the coast, put it on a tanker, ship it all the way around the world, drop it off at some other port, and then refine it, and then put it on a truck and deliver it to your local gas station, but if you have to pay $4 a gallon for that, that's ridiculous.
You lost me.
There's a lot less work that goes into making the milk than goes into getting the petroleum to turn it into gasoline, and yet we're complaining about $4 a gallon. Start putting that in perspective a little bit. What takes place before you get the gasoline? So even when they ship that stuff all the way around the world, it's crude petroleum. Okay? And it's like this really thick, nasty stuff, right? How many of you guys saw pictures after the
Oil spill?
the Deep Horizon oil spill, like you're in the Gulf, right? Really nasty, just thick little balls of tar, right? Well, what they do with that is they send it into this pipeline, right? You get this gigantic silo, and then you have this pipeline that comes in here, and it feeds the tar into the silo. And underneath the silo, you have this really hot furnace.
Let's make it
And then what happens is things in the petroleum start to separate based on densities. And then so you get these layers that start to form.
Like in the gems.
Exactly. And so these layers, then you have gasoline.
So you're saying
You have natural gas all the way at the top, right? And then you have this down here, which I think is somewhere in there is diesel, right? All this, and kerosene's in there as well. So this all gets separated from having to then boil the tar. And then you get the separating, and then so you have new pipelines that pop out. And that's how we get our different types of petroleum fuels.
Isn't the petroleum though?
And then, but then to ask them to do all this and deliver it to your local store for $4 a gallon is just, that's not very nice. How dare you charge me $4 a gallon for that?
Is it the same kind of concept like if you're cooking and like the oil separates from the food, or like if you have something and like it sits for a while and then like all the stuff settles at the top?
Perfect. That's a perfect example of fractional crystallization. In fact, my wife made a nice roast yesterday, and she didn't clean her dishes. So I get home late last night from work, and there's this thick layer of almost looks like wax, but it's basically all the fat that was in the roast, into the liquid, while it was warm. But then when it started to cool down, those fats started to crystallize, and then you get this layer that forms on top. That's a perfect example of fractional crystallization.
Isn't the petroleum, all that gas and stuff, the oil, isn't that what's cushioning between the plates?
No.